30 dB is a factor of 20 on a linear scale. So you will have to transmit the power that is 20 times higher than in free space to serve the user on the ground. Quite a difference.
In this equation, the D is squared.
Oh yes, indeed. Should be square. Yeah, yes. That was right. It's quite late. Oh. Better check my things. So sometimes I make mistakes. Okay. Questions?
No.
Okay. One last exercise for the day, because this will take some time.
One moment.
No, I won't like that. I just you should have already done. Thank you. May I?
Yes.
If I don't hear any screams. Okay. Another exercise and we are done. Okay, we are transmitting. You have an obstacle at 500 meters. This obstacle is 20 meters high. Then at other 500 meters, I know you use this for scanning. Multiple obstacles. This is 5 meters high. Then at 500 meters more, another obstacle, 50 meters, and the receiver is on the ground. Now I give you also the height of the transmitter. Receiver is on the ground, and the transmitter is located on a tower that is 10 meters high. Radio link at 900 megahertz. Over 2 kilometers per. But you have those obstacles. Those obstacles can be buildings in between. The question is, let's start with the simple things. Using Epstein-Peterson method, calculate the extra losses due to the obstacle, the diffraction losses. At least try to solve it, even if you don't arrive to the end. Try hard to solve it. Okay, let's solve this. After we end our day. First of all, we apply the tightrope to discard any discardable edges. So in this case, it will be something like that. So this edge can be deleted and neglected for the next calculation. Then the Eckstein-Peterson method, as you possibly remember, considers one edge at a time, considering as transmitter and receiver the two neighboring edges or whatever they are. So the first contribution to the losses is the one from this edge, and the baseline between the two is the one that I represented here. So the actual height of my obstacle is not 20 meters, but it's just the difference, the distance from the baseline. While for the other parameters, we can assume that the distance is 500 meters and this other distance is 1000 meters. There is not much difference because the distance is much bigger than those others. But we have to calculate this. Now, the best way to calculate this, in my opinion, is to calculate, if you think that this is the x-axis and this is the y-axis, the best way, in my opinion, is to calculate the equation of this straight line, that is simple, and then obtain this coordinate by entering this abscissa. The equation of the straight line is simply found because this would be something like let me use different words. Let me use the one. And we have to calculate A and B of those. Please note that I changed this because otherwise it can confuse it with this. Now, how do you do it? You do it by forcing this line to pass in this point and this point. So let's start from point A. Point A is x equals 0 and epsilon is equal to 10 meters. So you write for point A 10 is equal to 0 plus B. And then you force the line to pass through point B, and then you write the axis, the ordinate is 15, and x is 1,500. So actually, B is equal to 10, and there is no calculation to do. And from this, you got A equal to 5 divided 1,500. The slope is 0.00333. That's the equation of that line. So next you get the coordinate of this point. The abscissa is 500 plus B, using those values that we have found for A and B, that is 0.00333 times 500 plus 10. And you get, I have no idea, but I know the difference. So if you calculate that, yeah, you make me a pleasure. H1 is going to be 20 minus this value here. And I know this difference is 8.33 meters. So that's the height of the obstacle. So now we can calculate the Fresnel-Kirchhoff integral method like H1. The usual expression. 2 times 1 plus B2 where B1 is 500 meters. This is 1,500 meters. Divided 500 times 1,000. And if my calculations are correct, you get 1.12 for the Fresnel-Kirchhoff integral. Oh, sorry, there is lambda. This okay, too late at night. Sorry, lambda d1 times d2, and lambda is 33 centimeters. Sorry about that. No, it's better. Looks better. Okay. If you use the Lie approximation or the graphic, you get an extra attenuation that we call loss 01 of 15.3 dB. And this is the first contribution. Then there is another contribution from this is discarded. So the next contribution will be from this. When you consider this baseline. So for this is going to be H2, and the distance are D1 and D2. Now, to obtain the these coordinates, I would apply the same method by taking as this time as y-axis this, x-axis is this one. You calculate the equation of this line. I leave this to you as an exercise, but what you find, and you can do it at home, I give you just the result, you find H2 again 8.33 meters. It's just a chance, by chance. This time D1 is equal to 1,000 meters. D2 is 500 meters. And you end up with exactly the same value because you change D1 and D2, but the result does not change. This is absolute by chance. So the losses the Fresnel-Kirchhoff parameter would be 1.12, and the losses will be the same, 15.3. So total extra losses, L01 plus L02, 30.6 dB. Questions? Okay, enjoy your weekend.
Enjoy your weekend.
And see you on Wednesday. Miércoles, hasta miércoles.